Hello, my dear, and welcome to our astronomy course. Today, we have lecture number 12, and the topic of this lecture, we will be continuing studying the death of a star. What evidence do astronomers have that supernova 1987A formed a neutron star? The critical observation consists of only 19 neutrinos detected coming from the direction of the supernova. Because neutrinos are so difficult to detect, those 19 indicate that a huge flood of neutrinos passed through Earth just before the supernova was seen. Theory says the collapse of the core into a ball of neutrons should release a tremendous pulse of neutrinos. And astronomers link the neutrinos that were detected with the formation of that ball of neutrons. Notice that this evidence depends on a theory. That's not unusual, but scientists are very careful in analyzing such evidence to be so sure the background theory is right. Only then is the evidence meaningful. And now create a new argument. What evidence can you cite that type 1A supernova are not produced by massive stars? A nova appears to be a new star that becomes visible and then fades after a few weeks. Supernova are more luminous and last longer. Both are associated with the death of stars. Main sequence stars, like our Sun, can expand and become giant stars when they use up the hydrogen fuel in their. As that happens, the core contracts and heats up. Hydrogen fusion begins in a spherical layer around the core, a hydrogen fusion shell. Energy from the hydrogen fusion shell swells the star into a cool giant, 10 times larger in diameter than the Sun. Massive stars swell to become supergiant, up to thousands times larger in diameter than the Sun. The contraction of the star's core eventually ignites helium, first in the core and a bit later in a shell. If the star is massive enough, it can eventually fuse carbon and other elements. In degenerate matter, the density is so high that quantum mechanical effects prevent electrons from chaining their energy. Such matter is very difficult to compress, and its pressure does not depend on its temperature. If a star mass lies between about 40% or up to 300% solar mass, its helium core becomes degenerate before the helium ignites. Because pressure does not depend on temperature. There is no pressure-temperature thermostat to control the reaction. And when helium fusion ignites, the core simply explodes in a helium flash. All of the energy produced is absorbed by the star. As the giant star uses helium in its core and hydrogen in a shell, it moves towards the hot side of the HR diagram. Hot sides? Yeah, in a more blue color. As soon as it exhausts the helium in its core and begins fusing helium in a shell, it moves back towards the cool side, producing a loop in its evolutionary path. Yes, cool side. And you can see evidence of stellar evolution in HR diagram of star clusters. Stars in both open clusters and in globular clusters evolve in similar ways. The star begins their evolution at the same time, but evolve at different rates depending on their masses. The most massive stars leave the main sequence first and are followed later by progressively less massive stars. This makes the evolution of stars visible in the HR diagram. You can estimate the age of a star cluster from the turn-off point in its HR diagram. In all clusters, stars using helium follow a loop in the HR diagram that is visible in the diagram of star cluster as the horizontal branch. Red dwarfs, less massive than about 40% solar mass, are completely mixed and will have very little hydrogen left when they die. They cannot ignite a hydrogen fusion shell, and so they cannot become giant stars. They will remain on the main sequence for many times the present age of the universe. Medium mass stars, like the Sun, become cool giants and fuse helium, but cannot fuse carbon. They eventually blow away their outer layers and collapse into hot white dwarf. Ultraviolet radiation from the white dwarf ionizes the gas to produce planetary nebulae. White dwarfs cannot contract as they cool and will eventually become black dwarfs. The Chandrasekhar limit shows that no white dwarf more massive than 1.4 solar masses that can be stable. Presumably, more massive stars can become white dwarfs only if they shed mass. Close binary stars evolve in complex way because they can transfer mass from one star to the other. The two stars are enclosed by a dumbbell region known as the Roche lobe. If mass from one star crosses the surface of those lobes, the Roche surface, it can fall into the other star. The Lagrangian points in the rotating system are points where mass can remain stable. Matter can flow between the stars through the inner Lagrangian point, which connect the two Roche lobes. As a star becomes a giant, it can expand and fill its Roche lobe, spilling mass to the other star. Mass transfer explains why some binary systems contain a main sequence star more massive Zenith Giants companion, the Algol paradox. Mass that is transferred from one star to the other must conserve angular momentum and can form a whirling accretion disk around the receiving star. Accretion disks can become hot enough to emit light and even X-rays. Mass transferred onto the surface of a white dwarf can build up a layer of fuel that erupts in a nova explosion. A white dwarf can erupt repeatedly as long as mass transfer continues to form new layers of fuel. The evolution of the sun into a giant and then its collapse into a white dwarf will end life on Earth. Earth's more massive than about 8 solar masses cannot lose mass fast enough to reduce their mass low enough to die by ejecting a planetary nebula and collapsing into a white dwarf. Such massive stars must die more violent deaths. The massive stars on the upper main sequence fuse nuclear fuels one after the other, producing a layering of fusion shells. But such stars cannot fuse iron because iron is the most tightly bound of all atomic nuclei. When an aging massive star forms an iron core, the core collapses and triggers a supernova explosion known as a Type II supernova. The spectra of Type II supernova contain hydrogen lines, but the spectra of Type I supernova do not. At least two causes of Type I supernova are known. A Type 1a supernova can occur when the mass transferred onto a white dwarf pushes it over the Chandrasekhar limit and it collapses suddenly, fusing all of its carbon at once. A Type 1b supernova occurs when a massive star in a binary system loses its outer layers of hydrogen before it explodes. A supernova expels an expanding shell of gas called a supernova remnant. The supernova of AD 1054 produced a supernova remnant known as the Crab Nebula, which emits synchrotron radiation, evidence of a powerful energy source remaining inside the remnant. The supernova 1987A is only a few years old, but its expanding gases will eventually form a supernova remnant. Neutrinos observed coming from the direction of the supernova are evidence that the core collapsed and formed a neutron star. Now it's time to start new topics of today's lecture. It's neutron stars and black holes. You know, however a star lights, it must early die by collapsing into one of three final states: a white dwarf, neutron star, or black hole. Only three. These objects, often called compact objects, are small small monuments of the power of gravity. Almost all of the energy available has been squeezed out of compact objects. and you find them in their final high-density state. In this lecture, you must compare evidence and theory with great care. Theory predicts the existence of these objects, but by their nature, they are difficult to detect. To confirm the theories, astronomers have searched for real objects that can be identified as having the properties predicted by theory. That is, they have searched out real neutron stars and real black holes. No medieval knight ever wrote off on a more difficult task. A neutron star contains a little over 1 solar mass compressed to a radius of about 10 kilometers. Its density is so high that the matter is stable only as a fluid of neutrons. Theory predicts that such an object would spin a number of times a second and be nearly as hot at its surface as the inside of the sun and have a magnetic field 1 trillion times stronger than Earth. 2 questions should occur to you immediately. First, how could any theory predict such a wondrously unbelievable star? And second, do such neutron stars really exist? The neutron was discovered in the laboratory in February 1932. And physicists were immediately fascinated by the new particle. Only 2 years later, in January 1934, the Caltech astronomers published a seminal paper. Walter Barth and Fritz Zwicky showed that some nova in historical records were much more luminous than most, and suggested that they were caused by the explosive collapse of a massive star in an explosion they call a supernova. The core of the star, they proposed, would form a small and tremendously dense sphere of neutrons, and Zwicky coined the term neutron star. Over the following years, scientists applied the principles of quantum mechanics to see if such an object was indeed possible. Neutrons spin in much the way that electrons do, which means that neutrons must obey the Pauli exclusion principle. That means that if neutrons are packed together tightly enough, they can become degenerate just as electrons do. White dwarfs are supported by degenerate electrons, and quantum mechanics predict that an even denser mass of neutrons might support itself by the pressure of degenerate neutrons. How does the core of a collapsing star become a mass of neutrons? Atomic physics provides an explanation. Also, the outer parts of a star exploding as a supernova and blown outward, the core collapses inward. If the collapsing core is more massive than the Chandra-Dekkar limit of 1.4 solar masses, then it cannot reach stability as a white dwarf. The weight is too great to be supported by degenerate electrons. The collapse of the core continues, and the atomic nuclei are broken apart by gamma rays. Almost instantly, the increasing density forces are freed protons to combine with electrons and become neutrons. In a fraction of a second, the collapsing core becomes a contracting ball of neutrons. After the envelope of the star is blasted away, the core is left behind as a neutron star. Which star produces neutron stars? As we saw in the previous part of lecture, a star over 8 solar masses or less can lose enough mass to die by forming a planetary nebula and leaving behind a white dwarf. More massive stars will lose mass rapidly, but they cannot shed mass fast enough to reduce their mass below the Chandrasekhar limit. So it seems likely that they must die in supernova explosion. Theoretical calculations suggest that stars that begin life on the main sequence with 8 to roughly 20 solar masses will leave behind neutron stars. Stars more massive are thought to form black holes. How massive can a neutron star be? That is a critical question and a difficult one to answer, because scientists don't know the strength of pure neutrons. They can't make such matter in the laboratory, so its properties must be predicted theoretically. The most widely accepted calculations suggest that a neutron star cannot be more massive than 2 to 3 solar masses. If a neutron star were more massive than that, the degenerate neutrons would not be able to support the weight, and the object would collapse, presumably into a black hole. Two of the most massive neutron stars observed have masses of 1.94 and 2.74 solar masses, which confirm that. How big are neutron stars? Mathematical models predict that a neutron star should be only 10 or so kilometers in radius. Let's look to this slide, which combined with a typical mass means it must have a density of almost 1,015 grams per cubic kilo. Per cubic centimeter. On Earth, a sugar cube-sized lump of this material would weigh only 100 million tons. This is roughly the density of an atomic nucleus. So you can think of a neutron star as matter with all of the empty spaces squeezed out of it. Simple physics, the same physics you have used in previous module to understand normal stars, predict that neutron stars should be hot, spin rapidly, and have strong magnetic field. You have seen that contraction heats the gas in a star. As gas particles fall inward, they pick up speed, and when they collide, their high speeds become thermal energy. The sudden collapse of the core of a massive star to a radius of 10 kilometers should heat it to millions of degrees. Further, neutron stars should cool slowly, because the heat can escape only from the surface, and neutron stars are also so small, and they have a little surface from which to radiate. To conservation of angular momentum predict that neutron stars should spin rapidly. All stars rotate because they form from swirling clouds of interstellar matter. As a star collapses, it must rotate fast because it conserves angular momentum. Recall the example of the ice skater spinning slowly with her arm extended, and then speeding up, she pulls her arms closer to her body. In the same way, a collapsing star must spin faster as it pulls its matter closer to its axis of rotation. If the sun collapsed to a radius of 10 kilometers, its period of rotation would increase from once every 25 days to over 20 times a second. You might expect the collapsed core of massive star to rotate 10 or 2 or 100 times a second. It isn't hard to understand why a neutron star should have a powerful magnetic field. The gas of a star is iron, and that means the magnetic field cannot more easily through the gas. When the star collapses, the magnetic field is squeezed into a smaller area, which can make the field as much as 1,000,000,000 times strong. Because some stars start with magnetic fields over thousands times stronger than the sun. A neutron star would have a magnetic field as much as 1,000,000,000,000 times stronger than the sun. For comparison, that is about 10 million times stronger than any magnetic field ever produced in the laboratory. Theory predicts the properties of neutron stars, but it also predicts that they should be difficult to observe. Neutron stars are very hot. So from your understanding of black body radiation, you can predict they will radiate most of their energy in the X-ray part of the spectrum. Radiation that could not be observed in the 1940s and even 50s because astronomers could not put their telescopes above Earth's atmosphere. Also, the small surface areas of neutron stars mean that they will be faint objects. Consequently, astronomers of the mid-20th century were not surprised that none of the newly predicted neutron stars had been found. Neutron stars were, at that point, entirely theoretical objects. In November 1967, Jocelyn Bell, a graduate student at Cambridge University in England, found a peculiar pattern in the data from a radio telescope. Unlike other radio signals from celestial bodies, this was a series of regular pulses. Let's look to this graph. At first, she and the leader of the project, Anthony Davis, thought the signal was interference, but they found it day after day in the same place in the sky. And clearly, it was celestial in origin. Another possibility, that it came from a distant civilization, led them to consider naming it LGM, or Little Green Man. But within a few weeks, the team found 3 more objects in other parts of the sky pulsing with different values. the objects were clearly natural, and the team dropped the name LGM in favor of pulsar, a contraction of pulsing star. The pulsing radio source Bell had observed with her radio telescope was the first known pulsar. As more pulsars were found, astronomers argued over their nature. Periods range from 0.033 to 3.75 seconds and were nearly as exact as an atomic clock. Months of observation showed that many of the periods were slowly growing longer by a few billionths of a second per day. Whatever produced the regular pulses had to be highly precise, nearly as exact as an atomic clock, and gradually slowing down. It was easy to eliminate possibility. Pulsars could not be stars. A normal star, even a small white dwarf, is too big to pulse that fast. No could a star with a hot spot on its surface spin fast enough to produce the pulse. Even a small white dwarf would fly apart if it spun 30 times a second. The pulses themselves gave the astronomers a clue. The pulses lasted only about 0.001 seconds, placing an upper limit on the size of the object producing the pulse. If a white dwarf blinked on and then off in that interval, an observer would not see 0.001 second pulse. That's because the near side of the white dwarf would be about 6,000 kilometers closer to Earth. And light from the near side would arrive only 0.022 seconds before the light from the bulk of the white dwarf. And thus, its short blink would be smeared out into the longer pulse. This is an important principle in astronomy. An object cannot change its brightness appreciably in an interval shorter than the time light takes to cross its diameter. Its pulses from pulsars are no longer than 0.001 seconds. Then the object cannot be larger than 300 kilometers in diameter. Only a neutron star is small enough to be a pulsar. In fact, a neutron star is so small that it couldn't pulsate slowly enough. But it can spin as fast as thousands times a second without flying apart. The missing link between pulsars and neutron stars were found in late 1968, when astronomers discovered a pulsar at the heart of the Crab Nebula. Let's look to this lightly. The Crab Nebula is a supernova remnant, and theory predicts that some supernovae leave behind a neutron star. The short pulses and the discovery of the pulsar in the Crab Nebula were strong evidence that pulsars are neutron stars. Scientists often work by building a model of natural phenomena. Not a physical model made of plastic and glue, but an intellectual conception of how nature works in a specific instant. The astronomer's model may be limited and incomplete, but it helps them organize their understanding. The modern model of a pulsar has been called the lighthouse model and shown in the lighthouse model of a pulsar. Notice three important points. First, a pulsar does not pulse, but rather emits beams of radiation that sweep around the sky as the neutron star rotates. If the beams do not sweep over Earth, the pulses will not be detectable by Earth's radio telescope. And second, the mechanism that produces the beam involves extremely high energy and is not fully understood. And so, modern space telescope, observing from the above Earth's atmosphere, can image details around young neutron stars and even locate isolated neutron stars whose beams of electromagnetic radiation do not sweep over Earth. Neutron stars are not simple objects, and modern astronomers need both general relativity and quantum mechanics to try to understand them. Nevertheless, astronomers know enough to tell the life story of pulsar. When a pulsar first forms, it is spinning fast, perhaps 100 times a second, and the energy it radiates into space comes from its energy of rotation. So, as it blasts beams of radiation outward, its rotation slows. The average pulsar is apparently only a few million years old, and the oldest are about 10 million years. So, all the neutron stars rotate too slowly to generate detectable radio beams. You can expect that a young neutron star should emit powerful beams of radiation. The Crab Nebula is an example. Only about 950 years old, the Crab pulsar is so powerful it emits photons of radio, infrared, visible, X-ray, and gamma-ray wavelengths. Careful measurements of its brightness with high-speed instruments show that it blinks twice for every rotation. When one beam sweeps almost directly over Earth, astronomers detect a strong pulse. Half a rotation later, the edge of the other beam brushes over Earth, and astronomers detect a weaker pulse. Only the most energetic pulsar produce short wavelength photons, and thus pulse at visible wavelength. The Crab Nebula pulsar is young and powerful, and it produces visible pulses. And so does another young pulsar called the Vela, or as in Ukraine, we call Vitril. Pulsar, which located in the southern hemisphere constellation Well. Compared with the most pulsar, the Vela pulsar is fast, pulsing about 11 times a second, and like the Crab Nebula pulsar, is located inside a supernova remnant. Its age is estimated at relatively young, only 20,000 or maybe not more than 30,000 years. The energy in the beams is only a small part of the energy emitted by a pulsar. Roughly 99.9% of the energy flowing away from a pulsar is carried as a pulsar wind of high-speed atomic particles. This can produce small, high-energy nebula near a young pulsar. You might expect to find all pulsars inside supernova remnant, but the statistics must be examined with care. Not every supernova remnant contains a pulsar, and not every pulsar is located inside a supernova remnant. Many supernova remnants probably do contain pulsars, but their beams never sweep over Earth. Also, some pulsars move through space at high velocity. Let's look to this slide. Quickly leaving their supernova remnant behind. Evidently, supernova explosions can occur asymmetrically, perhaps because of the violent turbulence in the exploding core. And that can give a neutron star at high velocity through space. Some supernovae probably occur in binary systems and flying the two stars apart at high velocity. In any case, pulsars are known to have such high velocities that many probably escape the disk of our galaxy. And finally, you must remember that a pulsar can remain detectable for 10 million years or so. But a supernova remnant cannot survive more than about 50,000 years before it is mixed into the interstellar medium. For all these reasons, you should not be surprised that most pulsars are not in supernova remnants, and that most supernova remnants do not contain pulsars. Astronomers conclude that the February 1987 explosion of supernova 1987A formed a neutron star. As you read in the previous, as you know from the previous our lectures, a burst of the neutrinos was detected passing through Earth. And theory predicts that the collapse of a massive star's core into a neutron star produces such a burst of neutrinos. So the detection of the neutrinos is evidence that the supernova produces a neutron star. At first, the neutron star will be hidden at the center of the expanding shells of gas ejected into space. But as the gas expands and thins, astronomers might be able to see the neutron star. If its beams don't sweep over Earth, astronomers should eventually be able to detect its X-ray and gamma-ray emission. Also, no neutron star has yet been detected. Astronomers continue to watch the sky, hoping to see a new born pulsar. One reason pulsars are so fascinating is the extreme conditions found in spinning neutron stars. To see natural processes of even greater violence, you have only to look at the pulsars in binary. Over thousands of pulsars are now known, and some are located in binary systems. These pulsars are of special interest because astronomers can learn more about the neutron star by studying the orbital motions of the binary. Also, in some cases, mass can flow from the companion star onto the neutron star, and that produces high energy violence. The first binary pulsar was discovered in 1974 when astronomers Joseph Taylor and Russell House noticed that the pulse period of the pulsar PSR 1913 plus 16 was changing. The period first grew longer and then grew shorter in a cycle that took 7.75 hours. Thinking of the Doppler shift seen in spectroscopic binaries, the radio astronomers realized that the pulsar had to be in a binary system with an orbital period of namely 7.75 hours. When the orbital motion of the pulsar carries it away from Earth, astronomers see the pulse period length slightly erect. And then, when the pulsar rounds its orbit and approaches Earth, they see the pulse period shorter like a blue shift. From this changing Doppler shift, Taylor and House could calculate the radial velocity of the pulsar around its orbit, just as if it were a spectroscopic binary star. The resulting graph of radial velocity versus time could be analyzed to find the shape of the pulsar's orbit. Let's look to this slide. The analysis of PSR 1913 plus 16 showed that the binary system consists of two neutron stars, separated by a distance roughly equal to the radius of our sun. And yet another surprise was hidden in the motion of PSR 1913 plus 16. In 1916, Einstein's general theory of relativity described gravity as the curvature of space-time. Einstein realized that any rapid change in a gravitational field should spread outward at the speed of light as a gravitational radiation. Gravity waves have not been detected yet, but Taylor and House were able to show that the orbital period of the binary pulsar is slowly growing shorter because the stars are radiating orbital energy away as gravitational radiation and gradually spiraling towards each other. Normal binary stars are too far apart and orbit too slowly to emit significant gravitational radiation. Taylor and House won the Nobel Prize in 1993 for their work with binary pulsars. Dozens of pulsars have been found orbiting stars of various kinds. By analyzing the Doppler shift in their pulse period, astronomers can estimate the masses of the neutron stars. Typical masses are about 1.35 solar masses, in good agreement with model of neutron stars. In 2004, radio astronomers announced the discovery of a double pulsar, two pulsars that orbit each other in only 2.4 hours. The spinning beams from both pulsars sweep over Earth, as you can look at this slide. One spins 44 times a second, and the other spins once every 2.8 seconds. And this system is a pulsar jackpot, because the orbits are nearly the edge onto Earth. And the powerful magnetic field and the gas trapped in the field eclipse each other, giving astronomers a chance to study their size and structure. Further, the theory of general relativity predicts that these pulsars are emitting gravitational radiation, and that their separation is decreasing by 7 millimeters per minute. The two neutron stars will merge in 85 million years, presumably to trigger a violent explosion. In the meantime, the steady decrease in orbital period can be measured and gives astronomers a further test of general relativity and gravitational radiation. In addition to producing gravitational radiation, a neutron star's intense gravitational field means that binary pulsar can be sites of tremendous violence if matter is transferred from a star to a neutron star. The gravitational field is so strong that an astronaut stepping onto the surface of a neutron star, contact imaging, would be instantly smashed into a layer of matter only one atom thick. Matter falling into this gravitational field releases titanic amounts of energy. If you dropped a single marshmallow onto a surface of a neutron star from a distance of 1 astronomical unit, it would hit with an impact equivalent to a 3-megaton nuclear rocket. Generally, a particle falling from a large distance to the surface of a neutron star will release energy equivalent to 0.2 milliseconds square, where m times second square energy, if you remember, m c square. When m here we mean as a particle's mass at rest. Even a small amount of matter flowing from a companion star to a neutron star can generate high temperature and release X-rays, and gamma rays produce beams of X-rays that sweep around with the rotating neutron star. This you may see on a figure B on the right side of this slide. Earth receives a pulse of X-ray every time a beam points this way. The X-rays shut off completely over 1.7 days when the neutron star is eclipsed behind the normal star. Hercules X1 is a complex system with many different high-energy processes going on simultaneously. But this quick analysis serves to illustrate how complex and powerful such binary systems are during mass transit. The X-ray source for U18, 20, and 30 illustrates another way neutron stars can interact with normal stars. In this system, a neutron star and a white dwarf orbit their center of mass with a period only 11 minutes. Let's look to this slide in both sides, in figure A and B. The separation between the two objects is only about 1/3 the distance between Earth and the Moon. To explain how such a very close peering could originate, theorists suggest that a neutron star collided with a giant star and went into an orbit inside the star. Recall the low density of the outer envelope of giant stars. The neutron star would have gradually eaten away the giant star's envelope from the inside, leaving the white dwarf behind. matter still flows from the white dwarf into an accretion disk and then down to the surface of the neutron star, as you can see this on the right part on figure C. Objects called X-ray busters are thought to be such binary systems involving mass transfer to a neutron star. Notice the similarity between this mechanism and that responsible for nova. I think that enough for now. Okay, so any questions or propositions? As usually, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.